Proximal policy optimization. So, what is proximal policy optimization? Why do we need this? Uh, what led to the invention or creation of this improvement in our algorithms? We will discuss all that today. So, let's get started. Okay. So, why PPO? Same, it's proximal policy optimization. So why? So there was simple. We have algorithms based on value-based policy or value-based methods or policy-based methods, and there are improvements made to them, and those algorithms are used to solve uh, many environments or real world problems related to reinforcement learning. So one of those is a PPO. One of those key improvements is PPO, and so it allows for a faster and a more stable learning, and it's even more efficient. So the improvements are made to these simple algorithms based on these simple methods is to make them more efficient, faster, and stable. By stable, I mean it shouldn't collapse. Like even if you have solved the environment, after some time it collapses and goes to zero. The efficiency goes to zero, or the score goes to zero. So that shouldn't happen. It should be constant score, constant continuous score. And you might have seen this until now when you solved your projects as well, that when once you solve the environment, it goes up, the score goes up, you have solved it, and after some time it collapses. So that is not acceptable. It shouldn't happen, at least when you work in real life problems, real life projects. So to avoid that, improvements are made to basic algorithms based on these methods, and one of those improvements is proximal policy optimization. So our plan for today is to first review the basic policy gradient algorithm called reinforce, because PPO is an improvement on reinforce. Uh, so we'll first quickly review reinforce. Then we'll discuss the problems with the algorithm. Then we'll discuss why this problem arise and how to fix them, and that will lead us to the PPO. So so that's the plan. So first of all, reinforce, I'll quickly review it. So in reinforce, what we do is we reinforce good probabilities and discourage bad probabilities. So when I submit this, when I input this state to the network, it gives out some probabilities of taking different actions. Now here you can see left has highest probability. So the objective of reinforce is to increase its probability even more. So now it becomes zero point 0.6 and others become less. Similarly, and we increase the probability of the action with highest probability, because taking this action given this state in the end led to positive reward. Okay, so it increased the reward. So we want to improve or increase the reward even more. That's the point of policy based methods, that you want to increase the rewards more and more. That's why we increase the probability, so we'll get even higher rewards. If this was negative, or this, if taking this action led to reduction in total rewards, we would have decreased the probability of this action. That's what the reinforce algorithm does: increase good actions that lead to increasing R, decrease bad actions that lead to decrease in R. Overall, we want to improve our R and eventually our expected return for the environment. Okay, so this is a snapshot of the code from our reinforce coding exercise. And so I'll quickly go through the process of reinforce algorithm. So first we have random policy, so that means our initial parameters of the network. Then we collect a trajectory. So that is collecting over here one time step. So we initialize our parameters, we collect one trajectory, then we compute total reward for the trajectory for one time step. uh, so here, so we have initial, oh, I'll come to this soon. Let me finish this. So we compute total r, then we compute this function, the probability, log probability times r. So this is, again, to review, this is probability of taking action A given state st. So over here, so given this state, probability of taking, and I took this action, so what was that probability? So zero point 0.4. I actually took this action, so zero point 0.4. So that's what this is, pi theta atst. So probability of taking action A given state t, given these initial parameters theta without updating them. That's what this is. We take log of that and multiply by total reward from that time step. Sorry, from that, from that, yeah, one trajectory that we computed. Yeah, so one trajectory, and then we compute gradient by taking derivative of this function. Since this is constant, doesn't matter if you keep it outside or inside. So derivative of this function with respect to theta, so the parameters of the network, and that gives us g, and it's summed from t0 to end of the episode. So from, so t0, t1, t2, so it's summed. Then we get the gradient g, and then we update our parameters this way. And again, if increasing some parameter theta, some parameter in our network, if increasing that results in improvement of this whole function, that means I should increase that theta even more. That's what this function does, and it's exactly opposite of gradient descent. So this is gradient ascent, and we have discussed this many times in last few webinars. And then we repeat the whole process again. So how did we implement this in our code? So let's take a look at this. So this is our reinforce function, 1,000 episodes, max t 1,000, etc., etc. And so we start with a random state. The environment gives us a random state, and so we start our episode. Okay, that's one trajectory. So we get a state. We have a policy class that we made. This is an instance of the policy class. So we input state to our policy class, which includes the network, and it gives out action and log of the probability. So action to be taken and log of the probability of taking this action. Okay, and we're going to need this here. Okay, uh, and we saved them here. We take the action and we get next state reward, and we store them. So we get reward, and we collect rewards for all the time steps for this one episode, and we store them in this function reward, and then we have to compute a discounted reward. So what we are doing here is this with discounting factor. So we discount, and we have used this many times until now, since the very first code in the Monte Carlo methods. We create a list of this gamma to the power I, and then multiply them with each r, and then sum it. So that's what we are doing. So this is basically gamma 0, gamma gamma to the power 0, so that's 1. So 1 times r1 plus gamma 1, gamma to the power 1 times r2 plus gamma square times r3, and so on and so on, so on. So you know, so we are discounting it and then summing it. So that's our r. Now next part is this equation. So how do we compute the function first before we take the gradient. So that's what is happening here. uh, we are taking minus log prob because we are doing a gradient ascent. So log probability times total r. Remember, this is total r for the whole episode, not individual reward for each time step, and we got this from here. So minus of log probability times r, and then we take sum of all those. So summation of this log prob times r, and we are using minus sign here. We don't see minus sign, but we are using minus sign here because we want to do a gradient ascent, not a gradient descent. Okay, so once we get this, this is this function without the gradient. Then we have to compute its gradient, uh, and change the parameters uh, using the gradient. So all that is done in these three steps. Optimizer.zero grad makes all the gradient zero, not the parameters zero, all the gradients zero, and then we do this back propagation, that is taking derivative of this function or this function with respect to each parameter in the network, each weight in the network. And this step optimizer.step, what it does is it does this as well as it does some regularization as well. So taking gradients and this step is all done in these three. So this is how we implemented our process, and this is one loop, and we repeat this process again and again and again. So it's good to review and know and remember what we have done until now for reinforce. Next, so what was the issue with reinforce? So first of all, uh, people said that the gradient that we compute is very noisy, and I'll go into detail of this soon. And second is improper credit assignment. So that is the reward the reward we compute here for each time step. The people said that it's improper, it's incorrect, and update process is inefficient, trajectories are wasted. So that's true. We once we have computed these trajectories and done the whole loop, we don't use them again. We have to go start our another episode and collect new trajectories after updating our theta. That's the process here. We have one theta, we compute um, we compute a trajectory, one trajectory of n time steps, compute one trajectory, and we update our theta, and using that updated theta we have to compute new trajectories. So the previous trajectories that we uh, collected using previous theta are thrown away, and we have to collect new trajectories because we want to compute our new gradient using our new theta. That's more important for us. uh, so so people thought that there could be a way. Now this is mandatory. First of all, this is mandatory to have new trajectories if we have updated our theta, right? We shouldn't keep using old trajectories and try to update theta. Then theta will never change, never improve. So you have to compute new trajectories given new theta, and then you have to keep updating your parameters. So is there a way to not throw away the trajectories we computed using very initial theta? So that's what we will discuss, because that will be more efficient, and uh, the computational power that we used won't be wasted. That would be better use of our resources. So we'll see that how to do that. So first of all, noisy gradient. What's the problem with noisy gradient? Uh, so we have to compute these trajectories, right? Time steps and trajectory. We compute one, we collect one trajectory, and then we computed this return, right? Discounted return. and then we updated theta. Sorry, then we computed g from after every trajectory. Now, each of these trajectory are random and there is a high variance between them, as we have seen during the Monte Carlo methods, because as compared to TD methods, we don't go all the way, we just compute one time step and we guess it. But reinforce, as you might have noted on by now, follows a Monte Carlo process. So that means it collects all time steps, full trajectory, and then it computes its total return. So the problem is that each trajectory will be far away from each other, because even though you start with some random state in the beginning and they might not differ much, there are some random events happening in the middle that separate or disperse these trajectories from each other. So that's why our return will be different. So this whole function, so our rewards will be different. If we compute one trajectory, we get some reward. Next trajectory might be completely diverse, completely away from it. So first trajectory could be this and next could be this. And we collect this trajectory, compute G, and then we compute G and we update theta. And then in the next loop, suppose we collect this trajectory and then we compute G and then theta. So then the theta goes from this value to that value. So that's why it's very its value will be very noisy. That's what it means. The gradient G, uh, theta is noisy because the gradient G is noisy. Gradient G is noisy because we are going all the way to the end of the trajectory, and this trajectory have many random events in the middle that divide them, that make them so different from each other, and that's why G is going to be noisy and theta will be noisy. So we want to avoid that. So what can we do? Number one solution is, instead of just taking one trajectory and then computing G and then updating theta right away, we we first collect n trajectories, take average of this function of n trajectories, and then take its average. So what you have done here is collect n trajectories, take each of their gradient, and then take their average. Yeah. Or the other method is to normalize the R before we compute G. So again, collect n trajectories, find their mean, collect n trajectories, find the mean of the reward, find the variance or the standard deviation of the all the rewards, and then modify the rewards so that they fit into a normalized distribution this way. So suppose the mean of all the n trajectories of the so mean of the rewards of the n trajectories that we collected is 0, and suppose standard deviation is 1, then when you compute this new individual reward for each trajectory, all those rewards will fit in a normalized distribution, normal distribution. So either you normalize the r's of n trajectories, or you take derivatives, or you take the average of all those r's. So this will reduce the noise uh, of r and reduce the noise in G. Okay. So take, instead of just taking one trajectory, taking one r and computing G and then computing and then updating theta right away, collect n trajectories, average r, and then compute G of all those r's, all those trajectories together, and then take and then update theta, or collect n trajectories, normalize each r, and then substitute that r and those all those log probabilities here, and then compute g and theta. So that's the solution. Okay, problem number 2 was improper credit assignment. So what is this? So trajectory may contain many good or bad actions. So these actions are enforced or not depends only on the final total output. That's correct. So if we go back to this one, so whether this is improved or not, whether this is made from zero point 0.4 to zero point 0.6 or not, it depends only on this currently in the reinforced algorithm, right? Uh, but as per the our Markov process, the rules of the Markov process, uh, and this let me reverse a bit. So whether we improve this probability from zero point 0.4 to zero point 0.6 depends on total r, but this r might include time steps that are even before this time step. So this r might include reward from time steps before this uh, uh, time step, right? So the rewards before these time steps are also contributing to increasing or decreasing the probability of this function, right? And at the same time, the the reward from this time step will also contribute to increasing or decreasing the probabilities of the previous time steps. So that's not correct, because as per Markov process, this time step should only influence future actions. This the this time step shouldn't influence the previous actions before that time steps. Before that time step, it shouldn't influence previous time step. It should only influence future time step. That as per our Markov rule. So that's why the improvement that's made is to only use future reward. So in a Markov process, the action at time step t can only affect the future reward. It shouldn't affect previous time steps reward, right? Because it's like going back in time. So that's why the past reward, it shouldn't influence past. It shouldn't influence changing the probabilities of previous time steps. That's the whole point here. So that's why the improvement is to use only future reward. So instead of using all r's, we remove the past and only use future rewards in changing the gradient of any the in improving or decreasing the probability of any particular action given a state at that time step. So instead of using the sum, we only use future, right? And the reason is that Markov process, we by Markov process, this time step shouldn't influence the probabilities of previous time step. Previously we added all of them, took a capital R, and then that capital R controlled the probabilities of all time steps. But now we, for this time step to increase or decrease its probabilities, only future rewards will be included, not the past ones. Okay, that was the improvement number 2. Improvement number 3 is throwing away the trajectories. So our current process is that we and I also previously discussed this. We collect uh, trajectory. We start with policy, initial policy pi theta. Then we generate n trajectories now because we want to reduce noise. That's the improvement we incorporated. And then we compute a policy gradient g. And then we update it. That's the process. And so with theta, initial theta, we computed n we collected n trajectories. Please remember this. With theta, we collected n trajectories. And then we get new theta. Using this new theta, we have to again collect new trajectories and compute new gradient, because because that's how we will improve. We will know whether this updated theta is any good or not, or that's how we will know if we are going in the right direction in our gradient ascent, right? We can't just use, we can't update theta but use the same previous trajectories. We have to compute new trajectories. So what happens to the previous trajectories that we computed here? So they are thrown away, right? We don't use them. So this process, we throw away the trajectories generated during previous update step, which is inefficient, right? Because we are wasting, we are not properly using our computing resources. We are not properly using uh, our supply resources, power supply, everything, because we are doing the same thing again and again. Uh, but it's mandatory to do, to get new, to update, use the updated theta and compute g on new trajectory. It's mandatory, because that's how we will know if the update is going in right direction or not. That's our priority. But is there a way to make use of even the previous trajectories, to make use of previous trajectories, so that we could use our resources in more efficient manner? Is there a way to do that? So what if somehow we could recycle the old trajectories by modifying them so that they can be a representative of new policy? So is there a way to modify the old trajectories such that they look like being generated by the new theta, and then we can evaluate our new theta whether it's going in right direction or not? So is there a way to make old look corresponding to new? Yeah. So important sampling is uh, the solution to this. So in this, what we do is, suppose, so this is our new theta and this is our function of trajectory. So in our case it's r, reward r. And so, and this is the probability of having same trajectories given uh, new updated theta. So remember, this is not t prime, this is not tau prime, this is same tau. So what is the probability of having the same trajectory given new theta? So how do we, so this equation right now is incomplete. We need to modify this so that we can use the same previous tau, previous trajectories. So how do we do that is by using a reweighing factor. So what we have done here is nothing complicated. We multiplied by the ratio of p of t theta by p of t theta. So this is just one, p of t theta by t theta, and we multiply 1 by this, right? So this is the new uh, so this becomes a reweighing factor. So in this way we can still use previous uh, we can still use the same trajectory given the previous theta, but we just multiply it by a reweighing factor. So in this way we transform our old trajectories or probability of having old trajectory such that uh, they represent uh, so that they look as being generated using the new theta. And this is how we do that. We multiply them by a reweighing factor. And the simplification of this reweighing factor is that now theta tau is the same, so the trajectory is the same. So taking action given state 1 and taking action, this action given state 2, we are taking same action given same state. So these trajectories are same. The only thing changing is the probabilities of experiencing those states and those actions under new theta. So the probability of taking action A1 given S1 over probability of taking action, the same action given the same state, but with old theta. That's what this ratio is. This is with new theta, this is with old theta. and the total probability of having this trajectory given new theta, and this is the total probability of having the same trajectory given old theta. So that's what this is, and this is just a product of probabilities of individual time steps, right? Simple probabilistic equation, right? So how do we incorporate this in our main gradient function? So this is uh, this is our new gradient equation with theta prime, but this is incomplete because we are using the same t same so same trajectory, but using new theta, updated theta. So this has to be modified, this has to be improved, this has to be tweaked a bit. So we tweak it by multiplying by the reweighing factor. So given multiplying by reweighing factor makes it possible to use the same trajectory. Okay, that's what is happening here. And uh, I hope you have guessed how we got from log of this to this ratio. It's just a chain rule. So this is the derivative of uh, log of probabilities with respect to theta prime, right? And the derivative of log is 1 over that function times that. So this is just a chain rule. So let me quickly explain how we got from this to this ratio, because it can be a bit confusing, but it's simple chain rule. So me so suppose this is log of y of theta. So log of a function that is a function of theta, right? So log of y of theta, because probability this probability function of having taking action A given state S depends on theta. So let's call this y of theta, and then log of that. So it is log of function of y function of theta. And how do we take derivative of this with respect to theta is by chain rule. So first we take derivative of this with respect to y, because is the function of y. So d of the log of y of theta by dy times derivative of y of theta with respect to d theta. Sorry about the. I hope it's a bit clear. So we are considering this as log of y of theta. We are calling this as y of theta. This small function inside is y of theta, right? And we are taking its derivative with respect to theta. So first d of this with respect to dy, and then dy by the theta. So this first derivative of log of y of theta with respect to dy will be 1 over y d 1 over y. So that's what we get, 1 over y of theta. So this is 1 over y. You get it, right? 1 over y times dy by the theta. So, and that's what this is, dy by the theta. This thing represents dy by theta. So small, so uh, change in y of theta given small change in theta. That's what this is, and this is 1 over y of theta. So we get this by chain rule. Simple chain rule. And then we multiply by this RT future and everything, and the reweighing factor, of course, because we want to use the same old trajectories, but uh, use a new theta prime, right? And 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 then we simplify this as we have seen in the previous slide. This this is the simplification, so that we can cross them out. And also another assumption is that this so this becomes, and the rest became one, rest also cancelled out. When we saw here, we are only stuck with this and this and this. So what happened to other probabilities and the other what happened to this over this over this? Where did this go? Here. So we assume that this ratio is equal to, is closer to 1. They are not equal to 1, but the change in from theta to theta prime isn't that large, so that the probability of having this action uh, isn't very different than probability of having this action. So the ratio is almost 1. Same goes for these other ones. And this got cancelled, right? And we are stuck only with this. So these probabilities of taking, the ratio of the probabilities of taking this action will be given theta prime, and the probability of taking the same action given theta is very close to 1. So this ratio is very close to 1. Same goes for this and other one. That's why they disappeared, and we get this. So that's this, we get this equation with a condition that those theta to theta prime doesn't change so much, so that these ratios of probabilities are equal to 1. All these are closer to 1. And if they are like closer to 1.9, then this is 0.9999, closer, right? So the product won't won't affect the overall equation much. So that's what this is. That's why we get this. So now this is just, this is dy by the theta. So change in y theta given small change in theta on our y is this, right? Probability function. So small change in the probability given small change in theta over probability of taking that action in old theta. That's the ratio times RT future that we discussed previously. As per Markov, we can't use previous R, we only use future R's. Okay. Then we come to surrogate function. Surrogate means just a substitute. So what is the substitute if we want to use the same trajectories as theta, but for theta prime? So what is the new substitute for the previous function is this. So this is the surrogate function, probability of having this trajectory in theta prime given probability of having same trajectory in theta times RT. This is what they call surrogate function. And then we take, so this is the uh, new policy function that we want to uh, differentiate with respect to theta, that will give us G. That's why it's called surrogate, because it's the substitute. And then our new G will look like this. So this is our new G. It's just a derivative of the surrogate with respect to theta prime given theta. And also this comes with the condition that the theta prime shouldn't be very different from theta, such that the ratio of those probabilities are equal to 1 or closer to 1. Those are the conditions here. Okay. Right. So we have come to our the main part for PPO, that is clipping the policy updates. So the objective of policy based methods is to change theta such that we keep improving our expected return more and more and more. But uh, the change from theta to theta prime shouldn't be so large that the the expected return is improved unrealistically. This is unrealistic improvement in expectation. I call it unrealistic because you are testing, you are updating this, keeping in mind a particular environment, and any environment has an optimal level of expected maximum return it can reach, right? There is no infinitely increasing return. So but the theta shouldn't change so drastically that you get your rewards are expected return is improved to an unrealistic infinite level. And if it does, you might solve the environment, right? Because you are improving the expected return so much, but in reality your weight, your the model weight that you use on your testing environment might not give as good reward because it is not following a realistic curve, right? Because as per the actual environment, the reward should maximum reward should stop here. It shouldn't. It doesn't go beyond that. And in if you have done any classification problems, this is called overfitting. That you increase theta so well that it looks good during training, but while testing it collapses because it was overfit in the first place. So it's the same, not same but similar thing, that you in that case you reduce the loss, in this case you are improving the expected return. So you shouldn't try to improve the expected return so much that it it becomes unrealistically high and it won't even work in our testing environment. It will collapse. Your rewards will increase, and then they will collapse. You don't want to see this. Even for the project, you might have seen that your reward increases and then it suddenly collapses. That's what happens when you are just increasing your expected return during your training, right? So how to deal with this is to clip clip the change in theta such that it doesn't improve your expected return beyond this point. We have to clip it, and clipping is a very well-known process used for other deep learning applications. We clip gradients, right? If you remember, we clip gradients so that they don't collapse. They are stable. The model is stable during testing as well. So we clip the gradients. So that's what we will do here, but in a different way. So this is our expected return formula, and this is our surrogate function. This is our new g where we compute. So we change from theta to theta prime, right? Compute using same trajectory. So compute surrogate function and get a g, and this g will improve from theta prime to next theta prime, right? So the way to clip it is to clip this surrogate function's value. This is our surrogate function, and the whole process is that we have to uh, improve keep improving theta such that this value keeps increasing and increasing and increasing. But as I explained here, it can be problematic. So why don't we clip the value of this function such that uh, it the theta doesn't change so much that this value doesn't cross that clipping maximum. We have to clip this value. Instead of clipping the gradient value, we will clip the objective function's value. That's what we are doing here. So we are reducing the peak that you can reach. We are saying, we are telling the function, okay, this is the peak, this is the limit, don't improve, don't improve beyond this limit, this is the limit, you have done a good job, don't improve beyond this. That's what we are telling the objective function. Same, same thing in different, expressed in different way. So we are clipping here, we are telling the function, okay, good job, you reached here, don't go beyond this point, stop the update after this. And how to implement that is to use this function. So uh, clip, so we use an epsilon, and we say that don't let this function uh, improve beyond the value of 1 plus epsilon. Yeah, 1 plus epsilon. So we're clipping this to 1 plus epsilon. Epsilon is some small value like 0 0.1, 0 0.2, depending on the environment you can choose epsilon. So we are telling the objective function is keep improving theta. If you suppose theta was here, keep improving theta to theta prime until you reach this point. After this, stop updating. After this point, stop improving your parameters. Once your value of surrogate function reaches this point. And we use minimum because uh, at first your actual surrogate function's value might be less than this, so we use minimum of these two, and then we keep improving. After this point, the actual surrogate function value might go beyond 1 plus epsilon, but since you are using min, the objective function will look at this value and say, okay, I have reached my uh, max value, and the update will stop. So that's why we are using this. uh, so this is a new surrogate function, clipped surrogate function. Yeah, instead of just using the actual surrogate function, we use the clip surrogate function. Okay, so now we can summarize the proximal policy optimization process. So first, collect some trajectories based on some policy theta. Remember, initially we were collecting only one, but now we are collecting some n trajectories, so that we reduce the noise in G. We reduce the noise in G. Okay, and yeah, so some initialize theta prime as theta. So and then we compute the gradient of the clipped surrogate function. Now we are using clipped surrogate function, so that the update, so the objective function doesn't go beyond a certain point that we just saw. The objective function shouldn't pass a certain point. We are clipping it so that the values of theta don't change drastically. The update will stop here. Okay, so we get that G, then we update theta prime, and then we repeat step 2 and 3 without generating new trajectories. Okay, so we update, keep updating from theta prime to next theta prime to next theta prime 2 3 without generating new trajectories. Once we have repeated these two steps a few times, then we use the new theta to again compute new trajectories. Okay, and then we start over. So the whole process is take one theta, collect some trajectories, uh, and update theta to theta prime using clip surrogate function, and use the same trajectories for this step for a few times, 2 to 3 times, a few times, not two, a few times. Then collect new trajectories and again do the same thing. So we use the same trajectories for only these two steps. Once we have updated to theta prime a few times, we use the new theta prime to collect new trajectories. So the whole point of clipping uh, is only limited to these two steps. Okay. uh, and the same trajectories. Okay, so given same trajectories and theta, we come we we update from theta to theta prime by clipping the objective function. Then we collect new trajectories. Again, we clip the objective function, and again we update from theta prime to theta double prime. So the efficiency is improved. Uh, in previously we had to collect new trajectories for all the steps. Now we don't collect new trajectories that often. We do collect new trajectories. It's not that we just collect one set of trajectories and stick with it. We do collect new trajectories, but not that often. Okay, it's much less often now. Okay, so that's the whole point of PPO, right? Reduce noise and improve the process. And we also use in the clip surrogate, we have the RT future, right? So those three improvements are incorporated in here. So I think that's all for today's webinar. uh, if you have any questions, you can reach out to me on Slack. If you have any questions relating to these equations or the derivatives, simple, this is a simple chain rule. Some assumptions are made. So yeah, please reach out to me on Slack anytime. You can direct message me, and I will answer your question right away. So thanks. I will end the seminar now, and thanks, and have a nice day.